Salam, peace be upon you. My name is Muhammad Laif Siddiqui, the father of Holophase. Part 7. Topological Production. How the language generates knots, charges, and defects. 9.2.1. Defect Creation Rules. When smooth stories tear. Remember the drill. There is one field, phi, the holophase. One continuous cyclic movement from which all of reality unfolds. When phi begins to change, its first derivatives appear, and with them, the three dimensions show themselves at once: time as omega, space as k, and motion as v, built from both. Every higher derivative is a finer question about how phi changes, and each one casts three shadows together: a time shadow, a space shadow, and a motion shadow. These echoes mix and weave into one another, forming the patterns we call fields, particles, bodies, thoughts, and worlds. In this picture, everything that exists is a living tapestry of phi, endlessly echoing through its derivatives and their dimensional shadows. Today, we listen to just one of those echoes. We stand at a threshold within Episode 9, the Generative Grammar. In our previous climbs through Book 9.1, we became fluent in the production of smooth, continuous stories. We learned how a single phi configuration, through the recursive application of time and space questions, generates an infinite tower of derivatives, a perfectly smooth, flowing description of change. It was the grammar of flawless cloth, of seamless narrative. Today, we cross into new territory, Book 9.2, Topological Production. Here, we encounter the grammar of tears, knots, and stable imperfections. We discover how the language, without breaking its own rules, generates discrete, countable, persistent things from its continuous thread. Our guiding image for this walk is a living, growing tree. Specifically, the place where a branch meets the trunk. Not the smooth bark, but the knot. That whorled, complex grain where the tree's growth had to accommodate a limb, creating a permanent, unique pattern in the wood that no amount of sanding can erase. Picture yourself walking in an old forest, in the deep quiet of late afternoon. Light falls in shafts through the canopy. You stop before a massive, fallen oak. Its trunk is broad, its bark patterned with ridges and valleys. You kneel and run your hand along a cross-section where a great limb once grew. The grain of the wood does not flow straight here. It swirls. It forms concentric circles that bend and warp around the central point where the branch emerged. This knot is not a flaw in the wood. It is a record. It is the tree's response to a topological necessity: how to grow a continuous structure, the trunk, while also sending out another continuous structure, the branch, from a specific point. The smooth, linear growth could not continue unchanged at that junction. It had to develop this complex, whorled pattern, a defect in the simple grain, but a feature of the living tree. The knot is stable. It persists through the life of the tree and remains in the timber long after. It tells a story of growth and accommodation. This is the essence of topological production, the emergence of stable, identifiable structure from the resolution of a global constraint in a continuous field. Here, then, is the central puzzle of this part, phrased as simply as possible. How can a universe described entirely by a smooth, continuous field phi, a field that flows and changes without gaps, give rise to sharp, distinct, countable entities that persist through time? How do we get permanent things from seamless process? The answer has been waiting in the architecture we built in Episode 8, in the abstract concepts of winding numbers and the set called sigma. There, we learned that because phi takes its values on a circle, it is possible for phi to wrap around that circle as you move through space. This wrapping is measured by an integer, the winding number, a discrete quantity that emerges from continuous motion. That was a static, Platonic fact about the language. Now, in the generative context of Episode 9, this fact becomes a dynamic production rule. It becomes the mechanism by which the language generates defects. The rule is this: whenever the configuration of the phi field forces a non-zero winding number around the loop, the smooth description must fail somewhere inside that loop. That point of failure is a topological defect. The defect is not an added ingredient. It is the inevitable consequence of the field's global arrangement. It is the knot in the grain. So let us state the point clearly from the start. In the holophase language, Particles, charges, vortices, and other stable things are not foreign substances inserted into the phi-field. They are the phi-field itself, in specific knotted configurations where maintaining smoothness everywhere is mathematically impossible. They are not exceptions to the language. They are special sentences within it. Sentences with punctuation marks that cannot be removed without rewriting the entire paragraph. To understand this production, let's construct a simple mental picture. Imagine a vast, flat field covered with weather vanes. Each weather vane points in some direction, representing the local value of phi, an angle on a circle. In a calm, uniform state, all vanes point north. This is a trivial, smooth configuration. Now, imagine a different configuration. You stand at a central point and begin walking a large, perfect circle around it. As you walk, you carefully note the direction of each weather vane you pass. You discover something remarkable. By the time you complete the circle and return to your starting point, the vanes you have seen have rotated smoothly, and the vane at your finish points exactly one full turn, 360 degrees, different from the vane at your start. The field is continuous. There were no sudden jumps. Yet, this smooth, continuous arrangement has a global property. The total rotation around your path is +1. Now, try to imagine what the vanes must be doing inside the circle you walked. To have that smooth +1 rotation around the edge, the vane directions in the interior cannot all be well defined. There must be at least one point inside where the concept of vane direction breaks down. Perhaps at that point, the vane spins freely, or points in all directions at once, or simply cannot be defined. That point is the core of a topological defect. In this case, a vortex with winding number +1. The defect is forced by the global winding. You cannot have that smooth circular pattern with a +1 winding without having a singularity somewhere inside. This is not a physical law being imposed. It is a logical necessity of a continuous field on a circle. This is the defect creation rule in its purest form. In the precise terms of our language, phi maps from space, the manifold, to the circle S1. A closed loop in space is a path that ends where it began. We can ask, as we travel this loop, how many full times does phi cycle around the circle? The answer is an integer, n. This integer is the winding number. If n is not 0, then the map phi cannot be continuously deformed to a constant map over the entire disk bounded by that loop. There must be at least one point within that disk where phi is not continuous, a point in the defect set sigma. This is the topological guarantee. In production terms, if the evolving phi field develops a configuration with non-zero winding around some loop, then a defect is necessarily produced within that loop. The grammar itself generates the punctuation mark. Now, we must view this through triunity, for a defect is not merely a point in space. It is a full entity with temporal, spatial, and motional aspects, persistence and birth. A topological defect, once formed, exhibits temporal stability. Its winding number is a conserved quantity in many regimes. It cannot just fade away smoothly. To remove a +1 vortex, you must bring in a -1 vortex, an anti-defect, to annihilate it. This gives defects a kind of identity over time. Furthermore, defects can be created in time, not by magic, but through dynamical processes that force the winding number of a region to change from 0 to 1. This often happens through a phase slip or a spontaneous symmetry breaking event. The time shadow of defect production is the set of rules governing when defects can nucleate, how they persist, and when they annihilate within the sequence of configurations. Localization and structure. A defect is spatially localized. It is not smeared. Its core is a specific point or line. While the phi field is smooth almost everywhere, in an infinitesimal region around the defect core, the field varies so sharply that its spatial derivative, our k, becomes undefined or infinite. The spatial pattern around the defect is often beautifully ordered: spirals, radial patterns, or characteristic distortions. The space echo is the signature geometry that a defect imprints on the phi field in its neighborhood. It is the shape of the tier. Motion echo of a defect, dynamics and interaction. Defects are not static pins. They can move. A vortex can drift with the background flow. Two defects can orbit one another, governed by effective forces that arise from the distortions they create in the phi field. They can attract or repel. This motion is complex, but it is lawfully derived from the underlying dynamics of the phi-field itself. The motion echo is the kinematics of singularities, how these special points navigate the continuum that hosts them. It is the story of how punctuation marks can travel through the text. Thus, a defect is a triunified being, a persistent identity in time, a localized structure in space, and an interactive entity in motion. It is a full-fledged character in the narrative, generated entirely by the grammar of the underlying field. Let us now locate this on the master tree, our map of the Holophase language. We are ascending a robust essential branch that sprouts from the main trunk. This is the Topological Production branch. It depends on the root, phi, with its circular value space, S1, and on the smooth production engine of Book 9.1, which creates the patterns that can wind and twist. But this branch represents a different mode of generation. The recursive differentiation branch, DILDE, generates an infinite spectrum of qualitative nuance, ever more detailed descriptions of change. The topological branch, in contrast, generates discrete quanta and global constraints. It is the branch that produces countable things, one defect, two defects, a defect with charge plus 2. It enables the language to express concepts like identity, charge, and statistics. This branch is where the continuous analog language of phi learns to speak in precise digital integers. It is the bridge between the fluid verbs of change and the stable nouns of existence. To see that this is not an obscure mathematical trick, but a universal generative principle, let us place lanterns across the scales of reality. We will not list them, but weave them into our walk. Lantern from your daily life. The stubborn cowlick in your hair. After a shower, you try to comb your hair flat. It works almost everywhere. But there's that one spot, that whorl, where the hairs refuse to lie in a uniform direction. No matter how you comb, they insist on swirling around the central point. That cowlick is a topological defect in the orientation field of your hair strands. The strands themselves are continuous, but their preferred direction field has a non-zero winding around that spot. You cannot comb it away without cutting the hairs or permanently changing their growth pattern, an energetically costly operation. The defect is stable, localized, and a recognizable feature. It is produced by the topology of your hair follicles. This is defect creation on the scale of your body. A lantern from the laboratory. The quantized vortex in superfluid helium. When liquid helium is cooled to near absolute zero, it becomes a superfluid, a quantum fluid with zero viscosity. It can be set into rotation, but it cannot rotate like a normal liquid, spinning faster and faster smoothly. Instead, it develops quantized vortices. Each vortex is a tiny, hollow core around which the superfluid's quantum phase, its phi, winds by exactly 2 pi. The circulation around the vortex is precisely half ben Emer, a fundamental constant. You cannot have half a vortex. They are countable. 1, 2, 3 vortices. These defects are not impurities. They are topological features of the superfluid's own wave function. Their stability, quantization, and interactions are direct manifestations of topological production rules. This is defect creation in a pristine quantum system. A lantern from the cosmos. The concept of magnetic charge. In our familiar world, magnets always come with a north and south pole, a dipole. We have never found an isolated magnetic north pole, a magnetic monopole. Yet, in many grand unified theories of particle physics, such monopoles are predicted to exist as topological defects. They would arise as stable, point-like knots in certain fields during the early universe's rapid cooling. They would carry a quantized magnetic charge. Their existence is not postulated arbitrarily. It is a topological consequence of the fields involved, taking values on a more complex space than a circle, a sphere, for instance. The production of such a defect is a cosmic scale event, a punctuation mark written in the first sentences of the universe's story. Its search is one of the great quests in physics. Across the sink, the crystal, the superfluid, and the early universe, the same logical pattern repeats. A continuous field, a boundary condition or phase transition that forces a non-trivial winding, and the inevitable birth of a localized defect where the field cannot remain smooth. The defect resolves the topological tension. It is the universe's way of making a consistent sentence out of conflicting paragraphs. What then is the specific role of this defect creation rule within the Holophase language? It is a metagrammatical production rule. It operates at a level above the local derivative rules. It is not take the time derivative or take the spatial gradient. It is a rule that says, given the current global state of the phi sentence, a punctuation mark of type n must be placed here. It translates integral, global properties, winding numbers, into local, necessary structures, defect cores. It is the rule that allows the language to generate its own nouns from the verbs of change. The core question this part poses about phi is therefore, under what conditions does the smooth, differentiable description of phi break down, and what are the necessary, stable structures that appear at those breaks? This shifts our inquiry from how does it change to where does it necessarily become singular and what is born there. What does this rule do in practice? Let us name its functions with active verbs: to constrain, to crystallize, to conserve, and to characterize. It constrains the possible smooth stories. You cannot tell just any smooth story. If your story has a certain global twist, it must include a specific dramatic turn, the defect. It crystallizes fleeting patterns into persistent entities. A localized, high-energy fluctuation can snap into a topologically protected defect, turning a transient event into a stable object. It conserves discrete quantities. The winding number, the topological charge, often becomes a conserved quantity under smooth dynamics, providing a law of persistence for the defects. It characterizes different types of stable objects. A defect with winding +2 is fundamentally different from one with winding +1, not just in degree, but in kind. This provides a classification scheme for the nouns of the universe. Now we must discuss stability and the limits of this production. The defect creation rule holds and produces stable defects when two conditions are met. First, the field phi must be continuous and take values in a space that is not simply connected, like a circle where loops can get caught. Second, the dynamics must respect this topology. There must be an energy cost to smoothly unwinding the defect. If it costs too much energy to remove the winding, the defect is topologically protected. It's stuck. The rule breaks down or becomes irrelevant if the field's value space is topologically trivial, like a line where all loops can be shrunk, or if the field is not continuous. In the heartland of Holophase, a smooth, circle-valued phi field, this rule is a powerful, inescapable generator of structure. This brings us to the bedrock of the Holophase method: falsifiability. The topological production idea is not a pretty metaphor. It is a testable hypothesis about how certain structures arise in nature. The core claim: in any physical system that is accurately described by a smooth, circle-valued holophase field phi, every observed stable, particle-like defect, vortex, dislocation, flux tube, etc., must correspond to a region where phi is topologically non-trivial. This must be verifiable by measurement. If you track the phase phi along any closed loop enclosing the defect, the total accumulated phase must be an integer multiple of 2 pi. Conversely, in regions where careful measurement shows phi to be smooth and single-valued everywhere, zero net phase accumulation around all loops, no stable, localized defect structures should be observed. A detailed measurement scene. Imagine a state-of-the-art experiment in a low-temperature physics lab. The system is a thin film of a superconducting material. In a superconductor, the macroscopic quantum wave function again gives us a direct analog of a phi field, the phase of the Cooper pair wave function. When a magnetic field is applied, it can penetrate the superconductor in the form of abrikoso vortices. Each vortex is a tube of magnetic flux where the superconducting phase phi winds by 2 pi. The experiment involves a scanning superconducting quantum interference device, SQUID microscope. This exquisitely sensitive instrument can map both the magnetic flux, pinpointing the vortex locations, and through clever interference techniques, can also map the phase phi of the superconducting order parameter around those locations. The procedure is meticulous. First, they cool the sample and apply a known magnetic field, creating an array of vortices. The SQUID microscope scans the surface, producing two simultaneous maps. Map A shows the magnetic flux, revealing bright spots where vortices sit. Map B, derived from microwave or Josephson interferometry, shows the spatial pattern of the phase phi. The scientists then analyze Map B. For each bright spot in Map A, They choose a digital loop in the phase map that encircles it. They walk around this loop in the data, summing up the phase differences between adjacent pixels. They then ask, does the total phase sum around this loop equal 2 pi within experimental error? They do this for dozens of vortices, the pass condition, supporting the theory. For every clear vortex identified in the magnetic flux map, map A, the corresponding phase accumulation around the loop in map B is statistically indistinguishable from 2 pi or minus 2 pi. The values cluster sharply around this integer multiple. When they carefully warm the sample above its superconducting transition temperature and then cool it again in zero field, the vortices vanish. Subsequent phase maps show no localized 2 pi windings. The phase is smooth and single-valued everywhere. The correlation is perfect and reproducible. Topological defect in physical structure, 2 pi phase winding in the reconstructed phi-field. The fail condition, falsifying the theory. They find stable, well-defined vortices in the magnetic flux map, but the phase maps show no consistent 2 pi winding around them. The phase accumulations are random, or zero, or non-integer multiples of 2 pi. Alternatively, they might find clear, robust 2 pi phase windings in regions of the phase map where no corresponding vortex or any other defect-like feature appears in the magnetic, thermal, or density measurements. Either result breaks the proposed identity. It would demonstrate that for this superconductor, the stable vortex entities are not topological defects of the apparent order parameter field. This would force a re-evaluation. Perhaps the relevant phi field is something else, or perhaps the stability mechanism is not topological in this regime. This is how science progresses, not by defending the idea, but by exposing it to the hardest possible tests. This falsifiability thread is what turns a profound philosophical insight into a scientific research program. It creates a clear, empirical dialogue with reality. Let us now cultivate a recognition skill you can apply in your own observations. Look for topological defect logic in any context where a continuous medium or system must reconcile a local conflict with a global rule. Consider a tilting floor of dominoes. Imagine setting them all upright in a perfect grid, then trying to tip them so each domino leans toward its northern neighbor. This works in the middle of the grid, but at the edges, you'll find corners where this uniform rule cannot be satisfied. A domino would have to lean in two directions at once. The pattern must have a defect. This is akin to the famous hairy ball theorem. You can't comb a hairy ball flat without a cowlick. Watch cracks forming in aging plaster or in drying lake beds. The crack pattern is not random. It often forms connected networks that meet at specific points. These junction points are defects in the otherwise smooth stress field of the material. The cracks are the tears that relieve a topological tension caused by shrinkage. Analyze a traffic roundabout. The smooth flow of traffic, a velocity field, must accommodate the circular geometry. At the very center of the roundabout, the concept of traffic flow direction is undefined. The center is a defect core around which the flow circulates. The rule keep right works smoothly everywhere except at that singular point. When you perceive a stable, point-like or line-like feature that seems to be an unavoidable consequence of applying a smooth, continuous rule to a constrained geometry, you are witnessing the shadow of topological production. You are seeing a noun being generated by the syntax of the situation. Now, let us deeply connect this to our ongoing journey to the Holophase language. In episode 8, topology was presented as part of the abstract, Platonic architecture. Sigma as the grammatical boundary, winding as an abstract invariant, holonomy as semantic memory. Those were static properties of the language's library. Here, in the generative grammar of episode 9, these abstractions spring to life as dynamic production rules. The rule is active. If the evolving phi story develops a configuration with non-trivial winding, then a defect is produced at the necessary location. Its core is a point where the smooth derivative rules, the phi and the phi, of book 9.1 become inapplicable. We enter the domain of sigma. Yet, the defect as a whole object obeys a new, higher-level grammar of motion and interaction, which we will explore in subsequent parts. This is the majestic power of the language. It can generate the conditions for its own smooth rules to break down in a controlled, meaningful way, thereby creating a new class of stable entities. If you want to see the full mathematical formalism behind these ideas, the classification of defects using homotopy groups, the precise derivation of stability conditions from energy functionals, the differential geometry of the defect set sigma, you can search for Holophase on Zenodo. There you will find the scientific papers that this audio journey is built on. Let us now zoom out to see our position in the epic climb of episode 9. In book 9.1, we mastered the production of the continuous, the smooth, the wave-like, the verbs of existence. With this part, we have firmly stepped onto the branch of topological production. We have learned its first and most fundamental rule, defect creation via winding. We now understand that discrete, stable entities, the nouns of existence, are not primitive ingredients but are generated as necessary punctuation within the continuous narrative. This is a transformative realization. It is where the Holophase language begins to demonstrate its capacity to generate not just forces and waves, but things that have count, identity, and permanence. In the next part, we will see that these defects are social beings. They can have different integer charges, they can move through space, and crucially, they can weave around each other in time. This weaving, this braiding of defect world lines, leads to one of the most profound consequences of topological production, the emergence of quantum statistics. We will see how the simple act of exchanging two identical defects can leave a permanent memory in the global phase field, a memory that manifests as a phase factor of +1 or -1, corresponding to the fundamental distinction between bosons and fermions. The language, using only the topology of phi, begins to derive the very rules that govern the population of the particle zoo. As we conclude, hold in your mind the image of the tree knot. It is not a scar of damage, but a record of growth and adaptation. It is a complex, beautiful pattern born from the tree's continuous effort to grow both trunk and branch from the same living fiber. The universe, in the Holophase vision, is this growing tree. The smooth, flowing grain is the play of fields and forces, the verbs. The knots, the whorls, the defects are the particles, the charges, the stable structures, the nouns. They are not accidental blemishes on a perfect substance. They are the necessary, intrinsic, and stable features that arise when a single, continuous story is told with integrity across a complex manifold. The language has not just learned to describe knots, it has learned to tie them, creating the permanent landmarks in the flowing landscape of phi. Salam, and peace be upon you.